To make a neural network very easily in Python, you can use TensorFlow.Keras. It's an amazing library. It has a lot though. So they have a lot of different layers and it's very state of the art. We're not going to look at everything, but give a brief overview to all of them. So let's get started. Okay, so here I have the Keras Layers API documentation. So we can even see from TensorFlow.Keras import layers. So there's a whole bunch of different layers. I'm just going to go down to the bottom here. Okay, so first of all, we do have activations. So a activation is just kind of what function do we want to apply to the output of our neurons, whatever those types of neurons are. So maybe we want ReLU. Okay, that's kind of the state of the art of just some activation function that the point is to be nonlinear. Okay, these functions are nonlinear because if they were just linear, then it'd be like making a linear regression model, which is there's a time for that, but we don't want a linear model. We want a complex nonlinear model, and so basically we would stack many of these. We'll get to it right away, actually. Dense layers. Okay, so we would stack many dense layers, which is just a bunch of matrix multiplication with your parameters and your inputs, basically. And the point of that is to make the model more complex. So whatever you're trying to do, image classification, text classification, like NLP, computer vision, whatever it may be, you there's many times where you just want to make your model more complicated because the task at hand is complicated. Like it's hard to map the input to the output without a difficult function. So you do something like a dense layer with an activation function of say ReLU. Okay, and you don't actually have to apply these as different layers. Like you can just use the dense layer and you can specify that you want the activation function to be the ReLU or to be sigmoid or whatever it may be. Okay, so there's lots of layers here. Let's just get into it. So of course there's an input, it's what I use very commonly as the first layer, not always, but maybe it flattens it or maybe it extends the dimensions a little bit, like makes it from a 30 by 30 matrix to a 30 by 30 by 1 matrix or something like that, because different layers require different shapes. So you generally start with an input, and so embeddings, okay, that's actually something that's fairly complicated but extremely useful and not hard to apply at all in practice. If you haven't heard of an embedding layer, then I'm going to give you that this actually could really change the models that you make, because basically what an embedding does is it says, hey, okay, I want to map your input to some vector of a length that you can specify. So it's saying, okay, maybe we have the day of the year as a variable. So it's a number between, say, 0 and 366 or something like that. Okay, so the way you would model that is not through an integer itself, because you'd want to say if you're doing time series forecasting with the day of the year as a variable, it doesn't make sense for it to be 0 to 366 as like just an integer, because 0 and 366 are actually and 365 say, they're very, very similar numbers. Like basically that's saying January 1st versus December 31st. If you're modeling something like weather, like they're basically the exact same thing. So an easy way to deal with something like that is not to use one hot encoding, because technically it's a categorical variable, except that explodes the dimensionality like crazy. Like that's going to make your neural network really slow and hard to learn. So what you can do is use an embedding layer, and you can say, hey, I want to map this thing to some vector of, say, length 3. Okay, so then all of the numbers that you see in the input, like the 0, 12, 3, 365, 40, whatever it is, all those numbers, it's going to learn through gradient descent what vector of length, say 3, to actually represent that thing. And that's going to be a really good way of, no, it could be a really good way of turning your input that is a categorical variable to not a crazy high dimensionality, but still using it as a really meaningful feature. So embeddings, I believe they started because of in natural language processing. There's so many different words, and so we would need to map a word to a vector, basically. But they have evolved to be so much more useful than just NLP. Like definitely in time series forecasting, there's going to be a lot of categorical variables like that one. Okay, so I ranted about embeddings, but it's because I really think they're awesome and a lot of people don't know about them. So try an embedding if you haven't already. If you have a categorical variable, even if you think one hot encoding will work, just give it a try. Just experiment with it. You'll see that they can work really, really well. All right. So what else do we have? Masking? I actually don't know what that is, to be honest. I'll check that out later. Lambda, you can probably guess what a lambda layer is if you don't already know. It's basically you just map a function of your choice to it. Okay, so you can specify what you want to do. And I had to do this because I wanted to like multiply everything by 2 or something like that for some reason. So you might want to do that. Okay, so convolutional layers. If you're familiar with computer vision, then you're probably aware of convolutional neural network. God, tough word to say, man. Convolutional neural networks, CNN. I'll just call it CNN. So basically, the job of them is to very similar to a neural network. It's going to make the network or make the model much more complicated. Okay, so it's going to add complexity to the model, but its job is to keep in mind that the image is an image. Like the input is an image. That means it has like a spatial property, which essentially means the pixels in like higher top corner, for example, top right corner, they are very correlated with the pixels that are a little bit to the left. Like maybe we have a diagonal line on a cat. Okay, so if we can recognize cat images, then we'd recognize ears somewhere. Okay, so we should be able to find that ear wherever it is. This cat ear here, this cat ear here, to make a cat. And so if we basically slide a window, a moving window across the image, that's what a CNN does, then it's going to pick up on the features in that image and it's going to say, hey, oh, I think there's an ear here. They also use stuff like average pooling or max pooling, which is a way of kind of aggregating the results from the convolutional neural network to what they say downsample, basically. It's like, it's just aggregating results, grouping pixels together to aggregate. Okay, so that's the computer vision part. Okay, recurrent layers. So I'm going to talk about LSTM and GRU basically at the same time. I'm just going to talk about LSTM. Okay, so long short-term memory is what it stands for, and it's used in stuff like time series forecasting or natural language processing. So say for example we were doing sentiment analysis on a sentence, which basically means, give me a sentence and I want to try and figure out whether this is a good, like happy sentence or a not so happy sentence. So like, I hate you as a but negative sentiment, and I love you is a positive sentiment, but it gets more complicated than that. So say I'm scanning through the sentence, or my model is scanning through the sentence, and I'm at the last word, and I'm trying to figure out whether this whole sentence is, positive or negative. I can use an LSTM to try and figure this out because maybe I care about the whole sentence. Like maybe I care about what the beginning of the sentence was. Maybe I care what the second word and third word was, but maybe I don't. Okay, and I know that's kind of tricky, but long short-term memory. I have the ability to remember long in the past if I think that's relevant, but I have a short-term memory, meaning I can forget about this stuff very quickly. Like all of that stuff in the past, if I decide that I don't care, then I don't care. And what I mean by I don't care is my model, through gradient descent, through learning, supervised learning, it's going to figure out, do I care about the beginning of the sentence? Do I need to keep my long-term memory? Or can I just use short-term memory and say, no, actually, I just learned something very relevant and I don't really care anymore. For example, maybe we want the sentence, I hate people, but I think that people are very nice and I really enjoy them and they make me happy. So overall, I would say that's a positive sentence. And so the model would hopefully figure out the fact that that part of the beginning, let's just kind of forget about it because we saw stuff more recently that changed that result. But if you saw something like, I hate people, and also dogs are okay, and I think that this building I'm living in is all right, but so that's probably still a negative sentiment because at the beginning we said something really negative and we just said stuff neutral near the end. Pre-processing layers, so working with categorical data, image pre-processing, so maybe scaling everything, dividing by 255 to like normalize or standardize your features. And batch normalization, so that's something relatively new and you won't really have to see unless you're just trying to build like a CNN for fun. But they're extremely important and they're used in very complicated convolutional neural networks that you would use like transfer learning on, which basically just means you're borrowing this very complicated model. Say an exception or VGG network, then you would borrow you would borrow those networks when you're trying to make your own model, and it would be using batch normalization in there already. Okay, so regularization, stuff like dropout. Okay, dropout layer is its job, and it's very easy to apply. It basically just says, okay, give me a percent, give me a percent chance that I will drop out. And that means that if you apply those to these neurons, a layer of neurons, then they have, like, say, for example, a 20% chance of dropping out during training. So not during actually using them, like performing inference on the model, you're going to use everything, but on training, we might want to drop these neurons out. And that seems kind of weird. Like, why would you want to do that? The reason, and that's why it's called regularization, is basically to make the network not rely on any of these neurons too much, because what tends to happen in that case is we start to overfit the data. Okay, so we don't ever want to overfit the training data, because then what happens is, we're not able to generalize to new results. Okay, we never want to do that. So these are all about trying to do that. Dropout is the easiest to apply, probably. Reshaping layers, so there's stuff like changing the data, so changing the shape of the data, flattening it, so that's just a particular reshape where you basically get rid of the excess dimensions and you just stretch it out. And you might want to do that for like a CNN where you have something like a three-dimensional block of data, except you can think about that as just a long vector if you stretch it out. So maybe you want to flatten it like that. Padding and sampling and stuff like that. So that's going to be, again, for your convolutional neural network, most likely. Concatenate layers. So maybe you had like maybe your model took in an image and it took in a categorical variable and it took in a number. So then if you could concatenate these results, then you can merge to make a more complicated model. And it's so cool that Keras lets you do that. And it's really easy. So love that. I'm not going to talk about all of those. All the same idea again. It looks like we're at the end. So subscribe.